For our third question, and in this circuit, in the system, we are asked to find out the output CT if the input RT is a unit step. So here, the input, we got the Laplace transform of it. So on the time domain equivalent is given as UT. That's a unit step. And the Laplace transform of unit step is 1 over S. So our input is given as 1 over S because it's a unit step input. Okay, unit step function. So to be able to find the time domain equivalent of the output CT, first we need to find out CS. So here we have a simple negative feedback system. Let's first combine these two. We have RS as the input. And since this is a feedback system, the combination, negative feedback system, the combination of these two transfer function blocks, you can think a transfer function as 1 on the bottom path. So their combination is going to be the transfer function on the feed forward path, which is 5 over s squared plus 2s, divided by, since this is a feedback system, we got 1 plus, and the multiplication of both transfer functions, 5 over s squared plus 2s times 1. Now let's equalize the denominators here. So I'm going to multiply this one with s squared plus 2s. So we have 5 over s squared plus 2s from here. And for this part we have s squared plus 2s plus 5 over s squared plus 2s. So these terms will cancel out each other, and the transfer function or the combination of these two feedback system is going to be 5 over s squared plus 2s plus 5. So our system now looks like this. We have RS as the input, goes into the transfer function here, 5 over s squared plus 2s plus 5. And the output is CS. And since the input is a unit step function, the input is 1 over S. So the output is the multiplication of the input with the transfer function. So we have the formula for CS as 1 over S times transfer function 5 over S squared plus 2S plus 5. Okay. Now we can rewrite this as 5 over s squared plus 2s plus 5. Now to be able to find CT, the time domain equivalent of the output, we need to take the inverse Laplace transform of this function. To be able to do that, first we need to apply a partial fraction decomposition for both denominator multiplicants s and s squared plus 2s plus 5. So this can be rewritten as plus 2s plus 5 as one coefficient for multiplicand s, so we have a over s, and the second for this multiplicand, which is s squared plus 2s plus 5. Since the denominator is a second order polynomial, the equation we write down for the numerator should be 1 less degree. If this is a second degree polynomial, the equation we write here should be first order. So it's going to be bs plus c. Okay, the denominator here is first order polynomial, so the numerator is 0th order. It's like having 0 s to 0 multiplicand here. And since the polynomial here is second degree, the polynomial we write down for the denominator is first order. Okay, now we need to find out these three coefficients, a, b, and c. Let's equalize the denominators. So I'm multiplying here as with s squared plus 2s plus 5, and this one with s. So for this one, after doing so, all the denominators are going to be the same, so we are equalizing the denominators. Here we have a times s squared plus 2s plus 5, And here we have bs square plus cs equals 5. So for the square terms, we have s square and bs square. So we have a plus b should be equal to 0. And for the s terms, we got a times 2s, so we have 2a. These are the coefficients of s terms. And we got c plus c should be equal to 0. And for s to 0 term, or for the integer part, we got 5a equals 5. Okay, so a value is going to be 1 from this bottom one. And since a plus b is 0, b value is minus 1. And from the second equation, we got 2a, which is 2, plus c equals 0. So the value of c is going to be minus 2. So now we have rs and the transfer function, and we rewrote that as 1 over s plus minus s minus 2. Actually, let me rewrite this as this, minus s plus c is minus 2, but the negative sign is here, s square plus 2s plus 5. Okay. Let me see if I missed any point. No. Okay. So far so good. Now, for this part, it's easy because it's just the unit step function Laplace transform. But for this part, it looks a bit complicated. If you have such equations, it is quite probable that you are going to extract a sine and a cosine out of it. And for sine, the Laplace transform of sine, check, yeah, Laplace transform of, let's say, sine omega t is, let me try to remember, it was omega over s square plus omega square. And for cosine omega t, Laplace transform is, sorry, yeah, that's the correct form, s over s square plus omega square. Now this means for the Laplace transform of sine, whatever the term you have for the numerator, you have the square of it on the denominator as s square of some s term plus square of the numerator. And for cosine, numerator is s, so you got the square of the same term. If you have s plus 1, then the term here should be s plus 1 square. So you are taking the s terms square on the denominator plus square of some other term, omega square. So we need to find out or extract some s terms square out of this equation. It can be s plus 1 square, s plus 2 square, but it's going to be the square of some s term. And the same term should appear on the denominator with its square. Okay? So let me rewrite the equation we got up to now. We found that cs equals 1 over s minus s plus 2 over s square plus 2s plus 5. Now, if we convert this into s plus 2 square, we have s square plus 4s plus 4. Now we have too many s terms. We need to have 2s, but we have 4s. So this doesn't work. Let's try s plus 1 square. It is s square plus 2s plus 1, which is good. We got the s square term. We got 2s term. We have 5, but here we have 1. So in addition, we can write down square of 2. So we got 5 in total. So our equation now looks like this. 1 over s minus, since I wrote this term as s plus 1 square, I'm going to write down the same term on the numerator without its square. So since we have s plus 1 square here, I'm writing down s plus 1. So we need to have an additional plus 1 because we got plus 2 here. Divided by s plus 1 square plus square of 2. Now I'm going to divide this into two parts as s plus 1 divided by the numerator plus 1 divided by this same numerator. So now we have 1 over s minus s plus 1 over s plus 1 square plus square of 2 minus, because we get a negative sign here, 1 over the same numerator, s plus 1 square plus 2 square. Now if you compare these two equations with the Laplace transform of sine and cosine, this one looks like the Laplace transform of a cosine, right? Why? Because we have an s term on the numerator, and on the denominator we got the square of the same term plus square of some other term, same form. So we can say that the inverse Laplace transform of this part is going to be cosine. Omega value here is 2, right? Omega square, 2 square. So our omega value is going to be 2. So we got cosine 2t. But it's not enough, because if this function was s over s square plus 2 square, this should be the inverse Laplace transform. But as you can see, we got this additional plus 1 term here, and it converts into an exponential term, if you remember, on the time domain, and the formula was exponential t. So this additional plus 1 brings up an exponential term as exponential t, and the additional term is plus 1, and it goes to power expression with negative sign, so minus 1. Okay, so if you have an additional term right next to s rather than s, let's say you have s plus 1, s minus 2, whatever you got, this brings up an exponential term, exponential t, and you bring up this additional term to the power expression with opposite sign. We have plus 1, I added minus 1 for the power expression. Okay, so now we have the inverse Laplace transform of this part. This is a unit step function, so it's going to be 1. And for this part, it is kind of the Laplace transform of sine, but one term is missing. Here we have the omega square term. So our omega value is going to be 2. But if this is the case, the numerator should be omega. But we have 1, it should be 2. To do that, I'm going to multiply the numerator with 2 and divide the whole thing by 2. Okay? Because these two will cancel out each other, so the original function is still the same. But this helps us to create a function in the form of sine's Laplace transform. Right? We got omega square term here. Now we have 2 on the numerator, so that's the omega term. So this is the inverse Laplace transform of sine omega t, where omega is 2. Okay? And there's not going to be an additional term here. There's going to be additional term, because rather than s square, we have s plus 1 square. So same applies to here. This additional plus 1 term right next to s brings up an exponential term as exponential t. And whatever the value we got as the additional term goes to power expression with opposite sign. So this is plus 1. The term goes to power expression is going to be minus 1. So the inverse Laplace transform of this part equals this with an additional coefficient 1 over 2. So our inverse Laplace transform from 1 over s is unit step function, is inverse Laplace transform is 1. So for the next term we found exponential minus t times cosine 2t. And for the last part, we added an additional term as 2 times and 1 over 2. We used 2 to create omega term on the denominator, so this part remained. We have 1 over 2 times sine 2t times exponential minus t. And that's the time domain equivalent of the output of this system.